Hello viewers, welcome to another program on similarity. By this time, you must be familiar with what do we mean by similar figures. Two geometrical figures are similar when their corresponding sides are proportional and the corresponding angles are equal. However, in the case of triangles, the similarity is of special significance as one of the conditions obviously implies the other conditions. Now, before we discuss the application of similar triangles, let us have a first quick recap as to what similarity theorems were. If we have two triangles A, B, C and D, P, Q, R, angle B here is equal to angle Q, each being 70, angle C is equal to angle R, each being 50, and the third angle, angle A, obviously becomes equal to angle P. So, triangle ABC is similar to triangle PQR, and this similarity is known as AAA similarity. Now, besides this, we have another similarity theorem when there is a relation between the corresponding sides. Let us take two more triangles. Here the triangles are PQR and L, M and N. The ratio of side PQ is to LM is 1:2, QR is to MN is again 1:2, and the ratio of PR side to LN side is again 1:2. So, we say the triangles PQR is similar to triangle LMN, and this similarity is termed as SSS similarity theorem. Now, besides these, there is another case when we say the two triangles are similar. In that case, what happens is that the two sides are proportional and the angle included between these two sides is equal. So, here we have a triangle ABC and PQR. Side AB is to side PQ is 1:2. The ratio of side BC to side QR is 7:14, that is 1:2, and angle B is equal to angle Q, that is the angle included between side AB and BC is equal to angle included between the side PQ and QR. So, we say triangle ABC is similar to triangle PQR, and this similarity theorem is termed as SAS similarity theorem. So, these were the three basic similarity theorems. Now, we shall apply them today to solve some of the problems. Here first problem is regarding a trapezium. ABCD is a trapezium in which side AB is parallel to side CD and AB is 2 times CD. We have to determine the ratio of area triangle AOB and area triangle COD. Now, to look for the ratio of these two areas, what we need to do? Here we will have to establish that the two triangles AOB and COD are similar. Let us see how we establish them. AB here is parallel to CD and this is the transversal which cuts them. So, if this is the transversal which cuts them, then this angle becomes equal to this angle. Let us mark these angles. Let us name this angle 1 and this angle 2. So, angle 1 is equal to angle 2, and these are alternate angles. And if you happen to look at this angle, if we name it 3, then this will be equal to angle over here, that is angle 4. Again angle 3 is equal to angle 4 by the same reason, that is they are also alternate angles. And the third angle over here, angle AOD, is equal to angle COD. They are vertically opposite angles. So, we can say the triangle AOB is similar to triangle COD. And when the two triangles are similar, that means their corresponding sides will be proportional. And another property of similar triangles is that when the two triangles are similar, then their ratio of their areas is equal to the ratio of the squares on the corresponding sides. So, let us see the ratio of area triangle AOB upon area triangle COD. This will be equal to, corresponding to side AO is the side CO, corresponding to side AB is the side CD. So, we can say that this is equal to AB square upon CD square. Now, you may be interested in knowing that why we have not taken AO square. The obvious reason is because the relation has been provided to us between the side AB and the side CD. AB is 2 times CD, so we can replace AB by 2 CD. This is whole squared and upon CD squared, which on simplification will give you 4 CD square upon CD square. So, this ratio becomes 4:1. So, this is how we saw that by making two triangles similar, we applied the property that the similar triangles have their areas proportional to square of their corresponding sides. Again, now we are having another problem where the two triangles are on the same base. Here triangle ABC and DBC, they are on the same base BC, and such that angle A is equal to angle D. These sides BP and AC intersect each other at P. We have to show that AP times PC is equal to DP times PB. Now, here to prove this result, again we will go for the similarity of triangles APB and DPC. So, let us see the triangles APB and DPC. Angle A is equal to angle D, which is already given to us. Now, here the side AC and DB are intersecting each other at P. So, this angle will be equal to this angle, that is angle APB will be equal to angle DPC. They are vertically opposite angles. So, we see here, then obviously the third angle, this one, will be equal to this angle. The triangle APB is similar to triangle DPC by AA similarity. Now, when these are similar, that means their corresponding sides must be proportional, and so we get AP upon corresponding to AP is the side DP. This is equal to PB upon PC, and this is further equal to AB upon DC. Now, using this equality, that is AP upon DP is equal to PB upon PC, and cross multiplying them, we get the required result, that is AP times PC is equal to DP times PB. So, here in this problem again you saw that we make use of AAA similarity theorem to prove the required result. But in case a triangle is provided to you in which perpendicular has been dropped from the one of the vertex with a given condition, here the triangle ABC is there and the condition given to us is AD squared is equal to BD into DC. We have to prove that angle BAC is 90 degrees, that is angle BAC is a right angle. Now, to prove this result we will have to make use of again another similarity theorem to see that what similarity theorem we have to make use of. Here we are already provided that AD square is equal to BD into DC. So, if you happen to look at triangles ABD and CAD, we find that angle ADB is equal to angle CDA, each being 90 degrees. We are also provided that AD square is equal to BD into DC, and this result can be further interpreted as AD upon DC is equal to BD upon AD. Now, when we look at these triangles, that is ABD, ABD and CAD, we find that AD upon DC is equal to BD upon AD, and this angle included between them is each 90 degrees. So, we can say that triangle ABD is similar to triangle CAD. Now, which is the similarity theorem which we have applied? Here we have applied the SAS similarity. Now, if these are triangles are similar, then that means this angle, if I name it as 1, this will be equal to angle this one, that is, let us say angle 2, and angle this one, that is, if I name it angle 3, this will be equal to angle 4. So, we find that angle 1 is equal to angle 2, then angle 3 is equal to angle 4, for the obvious reason because the triangles are similar. So, their corresponding angles have to be equal. Now, adding these two, we get angle 1 plus angle 3 is equal to angle 2 plus angle 4. Now, 1 plus 3 is nothing else but angle A, and angle 2 here is angle C plus angle 4 here is B. But if you happen to look at the triangle ABC, you are familiar with that the sum of angles of a triangle, angle A plus angle B plus angle C is 180 degrees. So, replacing this angle B plus C by angle A, we find 2 times angle A is equal to 180 degrees, and from there we get that angle A is equal to 90 degrees. So, here we again applied the SAS similarity theorem to get at our required result. Now, by just looking at the right angle triangle, aren't you familiar with the right angle triangle theorem which was given by Pythagoras? The Pythagoras theorem states that in a triangle ABC, if there is this right angle, that is A is a right angle over here, then the square on the hypotenuse, that is BC square, is equal to AB square plus AC squared. Now, we will take up two problems based on this Pythagoras theorem, and here we will be making use of the Pythagoras theorem in a very special way. Here the first problem is triangle ABC is right angled at the point C if CD is perpendicular to AB and this CD, length of CD is denoted by P, AB, that is side opposite angle C, is denoted by C, and AC by B, this is the side opposite angle B, and BC by A, which is the side opposite angle A. We have to prove first that PC is equal to AB and 1 over P squared equals 1 over A squared plus 1 over B squared. Now, here to prove this result, what we will do? The first result we have to prove is that PC is equal to AB. So, let us see the triangle and find out its area. Area triangle ABC is equal to half base into height. If I take this as the base and this as the height, this will be equal to half A into B. But for the same triangle, if I take this as the base, that is AB as the base, then the corresponding height is CD, which is equal to P. So, this area can also be written as half into P into C. Now, since the triangle is same, so its area has to be equal in both the cases. So, we find that half AB is equal to 1 by 2 PC, which gives me the result PC is equal to AB. And that was the first result which was required by us. Now, in the second result, we have to establish the relation between P, A and B. So, let us see what P we get from there. P from here is AB upon C, and the same thing can be written as 1 over P is equal to C upon AB. If I square up this equation, I get 1 upon P squared is equal to C squared upon A squared B squared. But what C squared is? C is the side opposite to right angle. So, C squared must be equal to sum of the squares on the other two sides, that is AC squared and BC squared. So, that means this C squared can be replaced by A squared plus B squared upon A squared B squared, which on separating will give us 1 over B square plus 1 over A square. So, while proving the exercises on similar triangles or right triangles, we have to look for the given conditions very carefully and then apply some or the other theorem to get at the result. Now, here in another problem, we have a triangle ABC in which P and Q are midpoints of AC and BC respectively, and we have to show that 4 times AQ squared plus BP squared is equal to 5 times AB squared. Now, to show that this result, that is AQ squared plus BP squared, first let us see to which triangle AQ belongs. Now, here the AQ belongs to triangle AQC, where C is a right angle. So, we can write for that AQ squared is equal to AC squared plus QC squared. Similarly, if we happen to look at the side BP, BP is in the triangle BPC, and BPC is again a right triangle, right triangled at C. So, we have BP squared is equal to BC squared plus PC squared. Now, since our result we want AQ squared plus BP squared, so I will add these two equations. I will get AQ squared plus BP squared equals AC squared plus BC squared plus QC squared and plus PC squared. Now, remember here the condition was that Q is midpoint of BC. So, that means this QC can be replaced by BC upon 2, and P is the midpoint of AC. So, that means PC can be replaced by half of AC. So, making this transformation, we get AC squared plus BC squared plus BC upon 2 whole squared plus AC upon 2 whole squared, which on simplification will give us 4 times AC squared plus 4 times BC squared plus BC squared plus AC squared, and this will be equal to 4 times AQ squared plus BP squared, and this part becomes 5 times AC squared plus BC squared. Now, look at the relation between the side AC and BC. In the triangle ABC, this is a right angle. So, AB squared must be equal to BC squared plus AC squared. So, that means this part AC squared plus BC squared can be replaced by AB squared, and that becomes 5 times AB squared, and that was the result which we wanted to prove. So, once again you see that when we are solving a particular problem on similarity, we look for the given conditions and make the necessary replacements wherever they are necessary. But in case a special figure is given to us like an equilateral triangle, then we have to take into account the speciality of that figure. Here triangle ABC is an equilateral triangle and AD is perpendicular to BC. We have to establish that 3 times AB square, 3 times AB squared is equal to 4 times AD squared. Now, first let us go for this. The triangle ABC here is a right angle triangle. So, in case we see the triangles ABD and ACD, the hypotenuse AB is equal to the hypotenuse AC, because the triangle is given as equilateral, and AD is equal to AD, that is common to both triangles, and therefore, we have triangle ABD is congruent to triangle ACD. Now, once the triangles are congruent, that means their corresponding parts are equal. So, we can say from there that BD is equal to DC. This implies that BD is equal to DC. Now, we have to establish that AB squared, relation between AB squared and AD squared. So, let us look at the triangle ABD. Here this is a right angle. So, AB squared will be equal to AD squared plus BD squared. We have already shown that BD is equal to DC. That means BD can be written as BC by 2, BC divided by 2, and since the triangle is an equilateral triangle, AB is equal to BC is equal to AC. So, we can replace this BD by AB by 2 whole squared. Now, on simplifying this, we will get 4 times AB squared is equal to AD squared plus AB squared. And just by transposing this AB squared to the other side, we will get our required result. 3 times AB squared is equal to 4 times AD squared. And that was the result which we were interested in establishing. So, you have seen here that whenever we are talking of particular figures, we have to take care that the triangles or whatsoever figure is there, we have to look for the speciality of those figures. Now, let us take a case of a rhombus. In this rhombus ABCD, the diagonals AC and BD intersect at O. We have to prove that 4 times AB squared is equal to AC squared plus BD squared, that is which is the other diagonal. Now, to solve this problem, we have to take care as to what a rhombus is. Rhombus is nothing else but a quadrilateral whose all sides are equal in length. And the second property of rhombus is that its diagonals intersect each other at right angles, and the two parts of the diagonals are equal. That is to say that the diagonals bisect each other at right angles. So, let us make use of this property of rhombus and establish this result. Now, here because the diagonals bisect each other at right angles, that means this angle will be 90 degrees. So, if this angle is 90, the side opposite to it AB becomes the hypotenuse. So, we can write that AB squared is equal to OA squared plus OB squared. And can you recall by which theorem we are saying so? This is by Pythagoras theorem. And the other property of the rhombus is that diagonals bisect each other at right angles. That is, AO is equal to OC, or we can say that AO is equal to half of AC. Similarly, BO is equal to OD, or if we want to say OB, we can write it as half of BD, replacing OA by half of AC whole squared plus half of BD whole squared. On simplification, we get 1 over 4 AC squared plus 1 over 4 BD squared. And multiplying this whole equation by 4, we get 4 times AB squared is equal to AC squared plus BD squared. And that was the result we were interested in establishing. Now, here you saw that when we have special figures, we take into account its special properties. So, we learnt how to apply the similarity theorems and the Pythagoras theorems to solve various problems. In our next lesson, we shall discuss the constructions using similarity. Till then, goodbye.